Imagine looking at 96 feet of chart recorder paper every single day, scanning for patterns in what looks like radio noise, hoping to find something that shouldn't exist. Then one day, in the middle of all that static, you notice it. A quarter-inch of scruff that repeats, a signal so precise, so impossibly regular, that it pulses every 1.337 seconds like a cosmic heartbeat from a place where hearts can't beat anymore. Hello and welcome to the Sleepy Astronomer. Tonight we're drifting into a story about discovery and recognition, about a graduate student who found what no one was looking for, and about how the universe sometimes reveals its secrets to those who listen patiently. This is the story of Jocelyn Bell Burnell, born on July 15, 1943, who discovered pulsars, the collapsed hearts of dead stars that keep perfect time across the cosmos. If you're settling in for the first time, welcome to our gentle journey through the cosmos and the people who've helped us understand it. And if you've travelled with me before through distant worlds and cosmic mysteries, it's wonderful to have you back among the stars. Our journey begins not with a telescope pointed at the sky, but with a young woman building one with her own hands, 4 acres of wire antennas constructed over 2 years, designed to listen to the invisible universe. It follows her through months of careful attention, through the moment when the impossible became merely unexplained, through a discovery that would change astronomy forever, and then through an October afternoon in 1974 when the Nobel Prize was announced and her name wasn't on it. There's something profound about it, really. A discovery about collapsed stars, objects compressed by gravity into impossible density, made by someone whose own contribution would later be compressed, overlooked, and attributed elsewhere. Yet what endures? The prize that was given, or the pulsars that keep spinning, the institutional recognition, or the cosmic truth? In the Quaker tradition that shaped her, there's a teaching about the inner light, a quiet presence that remains constant regardless of outer recognition. Jocelyn Bell Burnell embodied this throughout her life, responding to injustice not with bitterness but with grace, and eventually turning recognition into opportunity for others. She found timekeepers in the sky that will outlast civilizations, and in her response to being overlooked, she showed us something equally enduring. If this story intrigues you, how the rhythm of collapsed stars mirrors the rhythm of a life lived with patience and grace, a gentle like or subscription helps others find their way to these nocturnal wanderings. So, find your most comfortable position. Take a deep breath, and let's begin our gentle drift through a life measured not in prizes but in pulsars, not in recognition but in revelation. A journey from a girl in Northern Ireland to the discovery of cosmic lighthouses that will keep pulsing long after we're all gone. Picture Belfast in the summer of 1943, where the smoke from German bombs has barely cleared and danger still hangs in the air like fog. Into this uncertain world on July 15th arrives a baby girl named Susan Jocelyn Bell, her first cry cutting through the heavy silence of a Quaker household where peace isn't just hoped for but actively practiced, even as the world tears itself apart. There's no cosmic announcement, no sign that anything significant has occurred. Just another birth in another family trying to maintain their values in a world that seems determined to abandon them. Her parents, Margaret and Philip Bell, are Quakers, members of the Religious Society of Friends, a tradition that emphasizes the inner light present in every person, the importance of listening more than speaking, the quiet practice of bearing witness. These aren't decorative beliefs for the Bells. They're principles that shape every decision, every interaction. in a society increasingly comfortable with violence and hierarchy, the Quakers insist on something else. That truth emerges from patient attention, that everyone has equal worth regardless of gender or station, that service matters more than recognition. Young Jocelyn, she'll go by her middle name, finding Susan a bit too common for her liking, grows up steeped in these values without quite realizing it. They're like the air she breathes, so constant she won't fully appreciate their influence until much later, when they help her navigate circumstances that might have crushed someone with a different foundation. But we're getting ahead of ourselves. First, there's childhood to navigate, and for young Jocelyn, that navigation proves surprisingly difficult. When she's 11 years old, she sits for the 11+ examination, one of those peculiarly British institutions that sorts children into different educational tracks, at an age when most of them are still figuring out how to exist in the world. Pass, and you go to grammar school, where academic subjects prepare you for university. Fail, and you're directed toward more practical training. Your entire future trajectory determined by a single test on a single day when you're barely old enough to tie your own shoelaces properly. Jocelyn fails. Picture that moment. The letter arriving, her parents reading it, the weight of institutional judgment settling onto a child's shoulders. According to the British educational system, young Jocelyn Bell isn't academic material. The test has spoken. The system has decided. She should pursue something more suitable to her abilities. Except her parents don't accept this judgment. Here's where those Quaker values start to show their strength. The Bells don't believe that a single test on a single day can capture the measure of a human soul. They don't believe that institutional decisions are necessarily correct just because they come from institutions. They know their daughter, curious, determined, thoughtful, and they refuse to let someone else's assessment override what they can see with their own eyes. So, they send her to a Quaker boarding school, where the educational philosophy aligns more closely with their own values, where questions are encouraged rather than suppressed, where being different isn't automatically treated as being deficient. It's a decision that will change everything, though nobody knows it yet. At school, something unexpected happens. Jocelyn discovers physics. Not the memorize these formulas kind of physics, but the universe actually makes sense kind of physics, the kind that explains why things fall, and how light moves and what holds atoms together. She's fascinated by it the way some children are fascinated by butterflies or dinosaurs. Completely, unreservedly, with an intensity that doesn't require justification or explanation. There's a problem, though. At her school, girls and boys take different classes. The girls learn about cooking and sewing, useful domestic skills for the lives they're expected to lead. The boys learn about science and mathematics. It's not meant maliciously necessarily. It's just how things are done, how society organizes itself, how gender roles get reinforced through 1,000 small decisions that add up to entire life trajectories. But Jocelyn wants to study physics, and here's where we see the first glimpse of something that will characterize her entire career. When faced with a closed door, she doesn't accept it as final. She asks if she can join the boys' science class. The school, to its credit, says yes. Maybe it's the Quaker philosophy at work, that equality thing they're always going on about. Maybe it's simple practicality. Either way, Jocelyn finds herself in the physics classroom, one of the few girls learning about forces and energy, and the mathematical language that describes how the universe actually works. She loves it. Not in some abstract, this will be useful for my career way, but with the pure joy that comes from understanding something true about the world. This is what makes sense to her, not the arbitrary rules of social hierarchy, but the elegant rules that govern how matter and energy interact. The universe, unlike human institutions, doesn't care about your gender. It just follows its own laws with perfect consistency, and anyone who learns the language can read those laws. She does well enough that university becomes possible. Glasgow University, where in 1961 she enrolls as one of the very few women in the physics programme. Picture the lecture halls, rows of young men and then, scattered here and there like rare birds, a handful of women who've somehow managed to navigate all the barriers between you shouldn't and here you are. The first time Jocelyn enters a physics lecture, the men, boys really, all of them barely past 18, whistle. Not a friendly greeting, but that particular kind of whistle that says you don't belong here, that treats your presence as entertainment rather than serious intention. It happens every time she enters a room that first year, every single time, like a ritual humiliation that everyone has agreed to participate in. She learns to arrive early, to already be in her seat when the others file in. A small adaptation, a minor strategy for navigating an environment that hasn't quite figured out what to do with women who insist on studying physics. It's not the last adaptation she'll have to make. But here's the thing about being an outsider. It teaches you to pay attention differently. When you can't rely on fitting in, when you can't take acceptance for granted, you learn to watch carefully, to notice details others might miss, to find your own way through problems rather than following the well-worn paths that weren't built for you in the first place. At Glasgow, Jocelyn encounters radio astronomy, a relatively new field that's revolutionizing how we observe the universe. Instead of looking at visible light, radio astronomers listen to radio waves coming from space. It's a different way of sensing the cosmos, one that reveals things optical telescopes can't see. Clouds of gas, distant galaxies, objects hidden behind dust. The universe, it turns out, is loud if you know how to listen. There's something beautifully democratic about radio astronomy. You don't need crystal clear skies or high mountain tops. You don't need perfect seeing conditions or expensive optical equipment. You just need the right kind of antenna and the patience to pass what the universe is saying through the static. For someone who's already learned to find signal in noise, who's already learned to navigate systems that weren't designed for her, it's a natural fit. She graduates in 1965 with a degree in physics and clear intentions. She wants to pursue a PhD in radio astronomy. And the best place to do that is Cambridge University, where Anthony Hewish is building something remarkable. Picture Cambridge in the mid-1960s, ancient colleges and modern science, tradition and innovation, rubbing shoulders on narrow streets where bicycles outnumber cars and the river carries punts full of tourists and students. It's a place thick with history and conscious of its own importance. Walking through those gates as a new PhD student must feel like stepping into a particularly demanding future. Jocelyn arrives to work with Hewish's group, which is building the Interplanetary Scintillation Array, 4 acres of dipole antennas designed to study quasars. Not to observe them directly, but to study how they twinkle, the way stars appear to twinkle when you look at them from Earth. Except with quasars, the twinkling reveals information about the solar wind, about space weather, about conditions between here and those impossibly distant objects. And here's where we need to understand something crucial about how science actually works, particularly in the mid-20th century. PhD students aren't passive learners sitting in classrooms. They're the hands and eyes of their research groups. They do the actual building, the actual observing, the actual data analysis. The supervisor, in this case Hewish, provides guidance and direction, brings theoretical understanding and institutional support. But the day-to-day work, the physical labour of science, that falls to the students. So Jocelyn spends 2 years building the telescope, not directing others to build it, but actually building it herself, along with the other members of the team. Picture her out in the fields near Cambridge, hammering poles into the ground, stringing wire between them, constructing an array that covers an area larger than Trafalgar Square. Her hands develop calluses. She learns which knots hold and which slip. She understands every component of this instrument because she's assembled it with her own hands. There's something profound about this kind of knowledge, the understanding that comes from building rather than just using. When you've constructed an instrument yourself, you know its quirks and limitations intimately. You know what it can and can't detect, where its sensitivity begins and ends. This knowledge will matter later, when she needs to distinguish between real signals and instrumental artifacts. By 1967, the array is operational. Every day it records radio observations on chart recorder paper, miles and miles of it, over 90 feet per day, a continuous record of everything the sky is saying in radio wavelengths. And every day, it's Jocelyn's job to analyze this paper, to look for the patterns and anomalies that might reveal something interesting about quasars. Picture her at her desk, day after day, scanning through these long strips of paper, looking at wiggly lines that represent radio signals from space. It's tedious work, the kind that requires sustained attention without guaranteed reward. Most of the time, you see exactly what you expect to see. The interesting moments when something unexpected appears are rare enough that you might go weeks or months without encountering them. This is where disciplined observation becomes not just a virtue, but a practical requirement. You have to care enough to keep looking even when nothing interesting appears. You have to trust that careful attention will eventually be rewarded, even though there's no guarantee. You have to cultivate what we might call active awareness. Not passive waiting, but engaged watchfulness. A state of alert readiness that can sustain itself through long stretches of apparent emptiness. And perhaps most crucially, you have to train yourself to notice when something is slightly off. Not dramatically wrong, not obviously anomalous, but just a little bit different from what you've been seeing. This requires a peculiar kind of noticing, not looking for anything specific, but remaining open to anything unexpected. These are the habits Jocelyn is developing during those long months of observation, not through any dramatic training or explicit instruction, but through the simple practice of looking carefully, day after day, at the signals the universe is sending. She doesn't know it yet, but she's preparing herself for one of the most important discoveries in 20th century astronomy. Not by trying to make a discovery, not by seeking glory or recognition, but simply by learning what sustained vigilance feels like. By learning to hear what the universe is saying, even when it's whispering, even when nobody else is listening. In ancient Quaker tradition, there's something called waiting upon the light, the practice of sitting in silence, trusting that truth will emerge if you're patient enough to let it. Jocelyn, sitting at her desk in Cambridge, scanning miles of chart recorder paper, is practicing something remarkably similar. Except she's waiting upon signals from collapsed stars she doesn't even know exist yet. The summer of 1967 approaches, warm and ordinary, with no indication that everything is about to change. Jocelyn continues her daily practice of observation, building up a mental catalogue of what normal looks like, what expected patterns feel like, what the baseline state of the universe appears to be through the lens of her 4-acre antenna array. And somewhere out in space, about 600 light-years away, a stellar corpse spins at impossible speed, its magnetic field sweeping through space like a lighthouse beam, sending out pulses of radio waves with metronomic precision. Those signals have been travelling toward Earth for 600 years, crossing the vast emptiness between stars, carrying a message that nobody has ever received before. They've been passing through human civilizations, through the Renaissance and the Enlightenment, through wars and revolutions and quiet moments of ordinary life. Completely undetected, completely unknown. Until a young woman in Cambridge, trained by circumstance to notice what others overlook, happens to look at her chart recorder paper on exactly the right day. But that discovery waits just ahead, in the summer heat of 1967, in a quarter-inch of what she'll later call scruff. First, there's this preparation complete, the building and the watching, the learning to see and the learning to listen, the slow cultivation of the habits that make discovery possible. Because here's a secret that rarely gets mentioned in the dramatic retellings of scientific breakthroughs. Discovery doesn't usually come to those who are looking for it. It comes to those who are looking carefully, without necessarily knowing what they're looking for. It comes to those who've developed the discipline to notice when the universe says something unexpected. It comes to the listeners. July 1967 arrives with the particular heaviness of an English summer, warm but not quite hot, humid in a way that makes the air feel substantial, like something you move through rather than simply breathe. Jocelyn sits at her desk in Cambridge, doing what she's done nearly every day for months now, analysing chart recorder paper. Picture the scene. The paper arrives in long, continuous strips, rolled up like ancient scrolls, covered in wiggly lines that trace the radio emissions from various parts of the sky. 96 feet of it every single day. If you laid out a month's worth end to end, it would stretch nearly 2,000 feet, more than half a kilometre of data requiring human eyes and human judgment to pass. Most of it looks exactly like what you'd expect. Radio sources produce characteristic patterns, some bright, some faint, some that scintillate in predictable ways as the solar wind passes between Earth and distant quasars. After months of looking at this paper, Jocelyn has developed an intimate familiarity with normal. She knows what ordinary looks like. She's built up a mental library of expected patterns. Which is why, when something isn't quite right, she notices. It's not dramatic, not some blazing obvious signal that jumps off the page demanding attention. Just a quarter-inch of what she'll later call scruff, a bit of recording that doesn't quite match the usual patterns. It appears during a scan of a particular section of sky, and then it's gone, buried in the continuous flow of data from all the other parts of the sky the telescope is observing. Most people would have missed it. Most people would have looked right past it, assuming it was interference from a passing car, or electrical noise from some nearby equipment, or any of the 100 small glitches that can appear in sensitive electronic instruments. The universe is full of noise, and distinguishing signal from interference is more art than science. But Jocelyn has spent 2 years building this telescope. She knows every component, every limitation, every quirk. She knows what instrumental errors look like. She knows what terrestrial interference produces. And this scruff, it doesn't quite match any of those familiar categories. So she makes a note, records the position in the sky where it appeared, then continues with her analysis, because there are 96 feet of chart paper to get through today, and this might be nothing at all. August arrives. The telescope continues its patient sweep of the sky, recording, always recording. And during another analysis session, Jocelyn sees it again, the same bit of scruff appearing in the same part of the sky. Now it's interesting. Once is happenstance. Twice is a pattern, or at least the beginning of one. Here's where the timing matters. If this were terrestrial interference, a car ignition, a piece of electrical equipment, someone's radio turning on at a particular time of day, it would appear according to solar time, according to clock time, at the same hour each day, perhaps, or at regular intervals that have nothing to do with where the stars are in the sky. But this scruff appears according to sidereal time, star time. It shows up when the telescope is pointed at the same patch of sky, regardless of what the clock says, which means it's not coming from Earth. It's coming from out there, from a fixed position among the stars. Jocelyn shows it to Hewish. "That's odd," she says, in what might be the understatement of the decade. "Look at this thing that keeps appearing in the same place in the sky, this thing that doesn't match anything we're supposed to be seeing." His initial reaction is dismissive, not unkindly so, necessarily. When you're running a research program designed to study quasars, and your graduate student shows you something that isn't a quasar, the natural response is, well, that's not what we're looking for. Interesting perhaps, but probably just noise. Probably nothing. But Jocelyn can't quite let it go. There's something about this scruff that doesn't sit right. It's too regular, too consistent, too much like a signal and not enough like noise. September. She sets up a high-speed recorder to capture more detail when the telescope next sweeps past that region of sky. The regular chart recorder moves too slowly to show fine structure. If this thing is pulsing rapidly, if it has internal detail, she'll need faster recording to see it. And then one day, she captures it. Not scruff anymore, but structure. Clear, unmistakable structure. The signal pulses. Not roughly, not approximately, but with a precision that would make a Swiss watchmaker weep. Every 1.337 seconds, a pulse of radio waves. Then silence. Then another pulse. Then silence. Over and over with a regularity so perfect it seems almost artificial. Picture Jocelyn looking at this recording, seeing for the first time what nobody has ever seen before, a cosmic clock, ticking away with inhuman precision, sending out its signal from somewhere in the depths of space. The universe doesn't usually work this way. Natural processes are messy. Stars flicker and vary. Galaxies pulse and change. Even the most regular natural phenomena have some variation, some wobble, some imperfection. But this thing, whatever it is, pulses with the kind of precision you'd expect from something engineered, something built, something designed. Which leads to an uncomfortable question that nobody quite wants to say out loud. Could this be artificial? Not that Jocelyn or Hewish seriously think they've discovered alien radio signals. That would be absurd, wouldn't it? But the precision is unsettling. Nothing natural should be this regular. Nothing in the messy, chaotic universe should tick like a metronome. So they check, and check again. Is this some kind of satellite? Soviet satellites were a genuine concern in 1967. The space race was in full swing, and who knew what the other side was putting up there? But satellites move across the sky. They don't stay fixed relative to the stars. And this signal comes from the same celestial coordinates every time. Is it equipment malfunction? Some oscillator in the electronics producing a false signal? But equipment malfunctions don't care about sidereal time. They don't wait until the telescope is pointed at a specific patch of sky before appearing. Is it interference from Cambridge itself? Some piece of machinery that happens to operate on a precise schedule? But Cambridge machinery operates on Earth time, not star time. And Jocelyn has checked. There's no correlation with any local activity. October arrives, and with it, more checking. The scientific method in action, though less glamorous than the textbooks make it sound. Just careful, methodical elimination of mundane explanations. Just the patient work of ruling things out one by one until what remains, however improbable, must be true. And then Jocelyn finds another one. Different part of the sky, different position entirely, but the same essential character, a source pulsing with extraordinary precision. This one has a period of 1.2 seconds, not exactly the same as the first, but close enough to suggest they might be related phenomena. Whatever these things are, there's more than one of them, which rather undermines the artificial signal hypothesis. If you were an alien civilization broadcasting to the universe, would you set up two transmitters pointing in completely different directions? Would you use slightly different pulse rates? It doesn't make much sense. Unless, and here's where the late-night speculation probably got a bit wild, unless there are multiple alien civilizations, all independently broadcasting, all using similar but not identical technology. They half-jokingly label the first source LGM-1, Little Green Men 1. It's a joke, mostly, a way of acknowledging the strangeness of what they're seeing without fully committing to any explanation. Scientists have to maintain plausible deniability after all. Can't go on record claiming you found aliens based on a few months of radio observations. But here's the thing about the alien hypothesis. It doesn't actually feel right. Not because aliens are impossible necessarily, but because the universe has shown itself to be far stranger than any intelligence might design. Natural processes, when you really understand them, tend to be weirder than anything we deliberately engineer. November, December. The checking continues. Jocelyn finds a third source, then a fourth, all pulsing with that same characteristic precision, but with different periods, different positions in the sky. The pattern is becoming clear. These aren't anomalies or flukes. They're a class of objects, a population, something the universe makes regularly, something that's been out there all along, just waiting for someone with the right equipment and the right attention to notice them. The math starts to come together. The theoretical framework begins to suggest itself. These can't be ordinary stars. Stars don't pulse this rapidly or this precisely. They can't be regular galaxies. They're compact, incredibly compact, to produce such rapid, regular pulses. And somewhere in the background of all this observation and verification, someone remembers that theorists have been predicting the existence of neutron stars for decades. Stars that have collapsed under their own gravity into objects so dense that a sugar cube-sized piece would weigh as much as Mount Everest. Stars compressed down to the size of cities, spinning rapidly, their magnetic fields sweeping through space like lighthouse beams. Nobody has ever seen one. They were theoretical constructs, mathematical possibilities that might or might not exist in reality. The kind of thing physicists propose because the equations allow it, not because they have any observational evidence. Until now. Until a graduate student in Cambridge, scanning 96 feet of chart paper every day, noticed a quarter-inch of scruff that didn't quite belong. By early 1968, they're ready to publish. Not because they've figured out everything, far from it, but because they have accumulated enough evidence to say, here's something new. Here's something the universe does that we didn't know about. Here are objects that pulse with extraordinary precision, and we're calling them pulsars because we're not entirely sure what else to call them. The paper appears in Nature on February 24, 1968. The authors are listed as Hewish, Bell, Pilkington, Scott and Collins, the research group that built the telescope and did the observations. Jocelyn's name is second, which in academic publishing signals significant contribution, but not primary authorship. The first author is the one who gets primary credit, the supervisor who directed the research. It's how the system works, how it's always worked. The student does the observations, the building, the day-to-day labour of science. The supervisor provides the theoretical framework, the institutional support, the scientific credibility, and when it comes time to assign credit, the supervisor's name goes first. Nobody questions this arrangement. It's normal, expected. The way the academic hierarchy organises itself. And Jocelyn, raised in a tradition that values service over recognition, the work over the credit, doesn't particularly question it either. She's made a discovery. She's contributed to human knowledge. The universe is stranger than anyone thought, and she's the one who proved it. That should be enough, shouldn't it? The announcement creates immediate excitement in the astronomical community. Radio observatories around the world turn their instruments toward the coordinates Jocelyn has identified. Within weeks, other researchers confirm the findings. The pulses are real. The precision is real. These objects exist. And then, the theoretical work begins in earnest. If these are neutron stars, and the evidence increasingly suggests they are, then they represent a completely new way to study physics under extreme conditions. Gravity so intense it crushes matter into exotic states. Magnetic fields millions of times stronger than anything we can produce on Earth. Rotation so rapid that the surface of these objects is moving at a significant fraction of the speed of light. From a quarter-inch of scruff to a revolution in astrophysics, from that's odd to the discovery of an entirely new class of stellar objects, from one graduate student's careful attention to a fundamental shift in how we understand what happens when massive stars die. There's something beautiful about the simplicity of the discovery process. No expensive new telescope needed, just attention to the data already being collected. No dramatic breakthrough moment, just the slow accumulation of evidence that something unexpected was happening. No genius insight, just disciplined observation and the willingness to take seriously a signal that others might have dismissed as noise. In ancient traditions of contemplative practice, there's often an emphasis on what's called beginner's mind, the ability to see things freshly, without preconceptions, without assuming you already know what you're looking at. Jocelyn, in some sense, had beginner's mind, not because she was inexperienced. By this point, she knew the telescope and the data intimately, but because she was willing to notice when something didn't fit her expectations. Most discoveries, if we're honest about it, come from this kind of attention. Not from brilliant theoretical predictions, not from building ever larger instruments, but from someone noticing that the data doesn't quite match what it's supposed to show, from someone paying close enough attention to see the anomaly, and curious enough to investigate rather than dismiss. The pulsars keep pulsing. Out there in space, stellar corpses spin and broadcast, their lighthouse beams sweeping through the cosmos with metronomic precision. They've been doing this for thousands or millions of years. They'll keep doing it for thousands or millions more. But now, for the first time in cosmic history, someone is listening. Someone noticed the pattern in the scruff. Someone paid attention to the signal that had been there all along, just waiting for someone patient enough to see it. Once you announce that you found something pulsing with impossible precision out in space, the theoretical physicists get involved. And when theoretical physicists get involved, things get interesting in the particular way that theoretical physics tends to make things interesting, by proposing explanations that sound more like science fiction than science, until you realize that the universe has always been stranger than fiction anyway. The question on everyone's mind: what could possibly pulse this precisely? What natural process could produce a signal that ticks like a cosmic metronome, keeping better time than the best atomic clocks humans have built? Thomas Gold at Cornell and Franco Pacini in Italy independently arrive at the same answer, almost simultaneously, in that way that sometimes happens in science when an idea's time has come. Neutron stars. Specifically, rotating neutron stars with powerful magnetic fields. Now, To understand why this explanation is both elegant and completely insane, we need to back up a bit and talk about what happens when massive stars die. Stars, for most of their lives, are in balance. Gravity wants to crush them down into nothing. The nuclear fusion happening in their cores produces outward pressure that resists that crushing. For millions or billions of years, these forces reach an equilibrium, and the star just sits there, peacefully burning hydrogen into helium, helium into carbon, and so on up the periodic table. But eventually, if the star is massive enough it runs out of fuel, the fusion stops, and suddenly there's nothing pushing back against gravity anymore. The core collapses. When we say collapse, we don't mean the gentle settling of a structure losing support. We mean catastrophic, instantaneous implosion. The core of a star, something with more mass than our entire sun, collapses in less than a second. In that second, matter gets compressed to densities that shouldn't be possible. Electrons get pushed into protons, creating neutrons. The whole core becomes essentially one giant atomic nucleus. Picture taking the sun, which is so large that over 1 million Earths could fit inside it, and crushing it down until it's the size of Manhattan. That's the kind of compression we're talking about. A teaspoon of neutron star material would weigh about 1 billion tons. If you could somehow bring a sugar cube-sized piece to Earth, it would weigh roughly as much as Mount Everest. The physics here is genuinely extreme. We're talking about matter in states that can't exist anywhere else in the universe, except perhaps in the cores of neutron stars and black holes. Pressures so intense that they squeeze atomic nuclei together until they're touching. Density is where the rules of ordinary matter break down and something else, something stranger, takes over. And here's the thing about this collapse. It's fast, extraordinarily fast, which means that anything the original star was doing, like rotating, gets intensified dramatically. It's the same principle as an ice skater pulling in their arms to spin faster, except instead of a person spinning a few times per second, you have a stellar core that was rotating maybe once every few weeks, suddenly spinning hundreds of times per second. The magnetic field gets intensified too. Stars have magnetic fields. Our sun has one. And when you compress a star down to neutron star densities, that field gets concentrated into something millions of times more powerful. We're talking about magnetic fields so intense they would rip the iron out of your blood if you got anywhere near them. Fields that can distort the shapes of atoms themselves. Now imagine this rapidly spinning, intensely magnetized neutron star. The magnetic field isn't aligned with the rotation axis. It's tilted. Like Earth's magnetic North Pole isn't exactly at the geographic North Pole, and this tilted magnetic field channels radiation out in narrow beams from the magnetic poles. So what you get is a cosmic lighthouse, a neutron star spinning hundreds of times per second, with beams of radiation sweeping through space. If one of those beams happens to point toward Earth during its rotation, we see a pulse. Then the beam sweeps away and we see nothing. Then it comes back around and we see another pulse. The precision comes from the fact that neutron stars are extraordinarily stable rotators. They're so dense, so massive, that once they're spinning, they keep spinning with almost no variation. The rotation period can be measured to extraordinary precision, not just seconds, but fractions of seconds. Better timekeepers than anything humans have built. This is what Jocelyn Bell Burnell discovered. Not just radio sources, but cosmic lighthouses. The collapsed hearts of dead stars still spinning, still broadcasting, mark in time with precision that will last for millions of years. Once the theoretical framework is in place, the implications start cascading through astrophysics like dominoes falling in slow motion. First, neutron stars actually exist. This might not sound revolutionary, But remember that they were pure theory before 1968, predicted in the 1930s by physicists who followed the math where it led, even though it led to conclusions that seemed absurd. Stars crushed down to city-sized objects, matter compressed to nuclear densities. It was theoretical speculation, mathematical possibility, the kind of thing that might exist, or might be an artifact of incomplete understanding. But now there's direct observational evidence. These things are real. The universe actually makes them. Massive stars actually collapse into objects so dense that a marble-sized piece weighs more than a cruise ship. Second, we now have laboratories for extreme physics that we could never create on Earth. Want to study matter at nuclear densities? Can't do it in a lab. You'd need to compress material with pressures beyond anything we can generate. Want to observe the behavior of matter in magnetic fields millions of times stronger than anything achievable with human technology? Good luck building that apparatus. But the universe, obligingly, has already built these laboratories, and it's broadcasting their properties to us in pulses we can detect from Earth. Pulsars become natural experiments in physics that goes beyond anything we can test directly. Third, general relativity finally has a testing ground. Einstein's theory predicts that intense gravity should do strange things to space and time, warp them, bend them, make clocks run at different speeds depending on how deep in a gravitational well they are. But testing these predictions requires gravitational fields much more intense than anything available in the solar system. Neutron stars provide exactly that. Their gravity is so intense that a person standing on the surface, if such a thing were somehow possible, would be flattened instantly. Time runs measurably slower near neutron stars than it does in empty space. Light bends noticeably around them. They're natural laboratories for testing whether Einstein was right about the fundamental nature of space-time. Fourth, and perhaps most practically, pulsars become cosmic measuring tools. Because they pulse so precisely and that pulse travels through space at the speed of light, astronomers can use them to measure distances across the galaxy. The pulse gets delayed slightly as it passes through clouds of gas and dust, and that delay tells us about the material between here and there. It's like having beacons scattered throughout the Milky Way, each one broadcasting not just its own existence, but information about everything between it and us. The interstellar medium, the thin gas and dust that fills the space between stars, suddenly becomes observable in new ways. We can measure its density, its distribution, its properties, all by watching how it affects pulsar signals. The galaxy becomes a little less invisible. Within months of Jocelyn's announcement, radio observatories around the world are searching for pulsars, and they're finding them. Dozens, then hundreds, each one adding to the catalogue of these cosmic lighthouses. Each pulsar is unique. They spin at different rates, some leisurely, taking a full second or more between pulses, others frantically, pulsing hundreds of times per second. They're different ages, some young, just thousands of years old, still spinning down from their violent birth, others ancient, billions of years old, their rotation gradually slowing under the drag of their own magnetic fields. They're scattered throughout the galaxy, concentrated toward the plane of the Milky Way where massive stars, the ones that become neutron stars, tend to form. Some are isolated, spinning alone in the darkness. Others are in binary systems, orbiting other stars or even other neutron stars in an intricate gravitational dance. Jocelyn's PhD thesis, when she completes it, is oddly titled The Measurement of Radio Source Diameters Using a Diffraction Method. It's about the original research project, the quasar observations the telescope was designed for. The pulsars, the discovery that will define her career, the finding that changes astrophysics get barely a mention, because technically they were someone else's project. Hewish's project. She was just the graduate student who happened to notice them. This is how academic science works, how it's always worked. The student does the observations. The supervisor gets the credit for the discovery. It's not personal. It's not malicious. It's just the system, the hierarchy, the way things are organized. And nobody questions it, because everyone has agreed, implicitly, that this is how things should be. Jocelyn finishes her PhD and moves on. Southampton first, to work on X-ray astronomy. A new field, new questions, new instruments to master. The pulsars keep pulsing. The scientific community keeps studying them. And Jocelyn Bell Burnell, having made one of the most important astronomical discoveries of the 20th century, goes on to the next stage of her career. Because here's something that doesn't get said often enough about scientific discoveries. The moment of discovery is often less important than what comes after. The finding itself is dramatic, yes, but the real work is understanding what you've found, figuring out its implications, building the theoretical framework that explains it. And that work, the work of understanding, is collaborative, distributed, involving hundreds of scientists across decades. One person notices the anomaly, others figure out what it means, still others explore the implications, test the predictions, build new instruments to observe in new ways. The pulsars that Jocelyn discovered are still being studied today, more than 50 years later. They've revealed secrets about neutron star physics, about supernovae, about the life cycles of massive stars. They've tested general relativity to extraordinary precision. They've helped us map the galaxy and understand the medium between stars. Some of them, binary pulsars orbiting other neutron stars, have even provided indirect evidence for gravitational waves, ripples in spacetime predicted by Einstein, but not directly detected until decades after Jocelyn's discovery. The 1993 Nobel Prize in Physics would eventually go to the discoverers of such a binary pulsar system. Not Jocelyn's pulsars, but systems found because people knew to look, because she'd shown that these objects exist. There's something beautiful about the simplicity of what pulsars are beneath all the complex physics. They're endings that keep broadcasting, deaths that mark time, the catastrophic collapse of massive stars transformed into something stable, something enduring, something that will keep spinning and pulsing for billions of years. Order emerging from chaos, precision arising from violence, the universe taking destruction and creating from it the most accurate clocks in the cosmos. In some traditions, there's a concept of wisdom arising from suffering, of clarity emerging from chaos, of the way difficulty can refine rather than destroy. Pulsars are, in their way, a physical embodiment of that principle. Massive stars die violently, catastrophically, in explosions that briefly outshine entire galaxies. And from that death comes something that pulses with perfect regularity, that marks time with precision that will outlast civilizations. The universe doesn't care about metaphors, of course. Pulsars aren't trying to teach us anything. They're just physics, playing out according to the laws that govern matter and energy and space-time. But there's something quietly profound about them, nonetheless. Something about the way collapse creates stability, the way destruction produces precision. Jocelyn, moving on to study X-rays and infrared and millimeter-wave astronomy, carries with her the knowledge that she found these objects, that she was the first to notice the pattern, the first to take seriously the scruff in the data that others might have dismissed. That discovery is hers, regardless of whose name appears first on papers, regardless of who gets credit in the official hierarchies of science. The pulsars know who found them, or they would if pulsars could know anything. But they can't, of course. They just keep spinning, keep broadcasting, keep marking time with their impossible precision. Somewhere out there, about 600 light-years away, that first pulsar, the one that appeared as a quarter-inch of scruff in July 1967, continues its patient rotation. Once every 1.337 seconds, its lighthouse beam sweeps past Earth. Most of those pulses go undetected, unreceived, just radiation streaming through space with no one listening. But some are caught by radio telescopes, added to databases, used by astronomers studying everything from neutron star physics to the structure of the galaxy. The signal that Jocelyn Bell Burnell first noticed in the summer of 1967, the scruff that didn't quite fit the expected patterns, has become one of the most studied objects in astronomy. Not because it's the brightest or the closest or the most unusual pulsar, but because it was the first, the one that proved these objects exist, the one that changed everything. And still it pulses, patient and precise, a cosmic clock marking time that nobody asked it to mark, serving as a lighthouse that nobody built, broadcasting to a universe that largely doesn't listen. Except for one person who did listen, who noticed, who paid attention when everyone else was looking somewhere else. The revelation is complete. Pulsars are neutron stars, collapsed stellar cores spinning impossibly fast, marking time with precision that will outlast mountains and continents, and perhaps even the species that discovered them. But another revelation waits ahead. One that has nothing to do with physics or cosmic clocks or the nature of collapsed stars. A revelation about human systems, about recognition, about what endures and what doesn't when the prizes get handed out. October 1974 arrives with a particular crispness of autumn in England, when the leaves are turning and the air carries that first real hint of winter. Jocelyn Bell Burnell is working at University College London now, having moved through several positions since finishing her PhD, building a career in X-ray astronomy. She's married to Martin Burnell, has a young son, is navigating the same impossible balance that many women in science attempt: family and research, and the constant sense that you're not quite doing either one well enough. The Nobel Prize in Physics is announced on October 15th. Two names, Anthony Hewish and Martin Ryle. Hewish for his decisive role in the discovery of pulsars. Ryle for the development of aperture synthesis, a technique in radio astronomy. Both Cambridge professors, both senior scientists, both men whose work has undeniably advanced the field. Jocelyn Bell. Burnell's name is not on the list. Picture that moment. The announcement reaches her, probably through a colleague, possibly through the news, the way these things ripple through the scientific community. The Nobel Prize has been awarded for the discovery of pulsars, the discovery she made. The objects she first noticed in the chart recorder paper, the signals she tracked and verified and confirmed, weren't instrumental artifacts or terrestrial interference. She reads it, absorbs it, then returns to work. She does not appeal. She does not campaign. She does not withdraw. At first, there's no public statement from her, no immediate reaction recorded for posterity, just the continuation of her research, the ongoing work in X-ray astronomy, the daily practice of being a scientist who happens to have made one of the most important discoveries in modern astronomy and has now watched the highest honour in physics go to someone else. The press notices. Of course they notice. It's the kind of story that writes itself. Female graduate student makes groundbreaking discovery. Male supervisor wins Nobel Prize. The optics are, to put it mildly, not great. Fred Hoyle, the distinguished astronomer who has his own complicated relationship with Nobel recognition, publicly calls the omission a scandal. He argues quite clearly that Bell Burnell made the actual discovery, that she's the one who noticed the signal, who insisted on investigating it despite initial dismissiveness, who did the careful work of verification. Other astronomers weigh in, some publicly, more privately. The conversations in university hallways and coffee rooms, the letters exchanged between colleagues, there's a general sense of discomfort. Not universal, perhaps. Many people defend the decision, argue that the Nobel Committee got it right, point to the traditional understanding of how credit works in supervisor-student relationships. But enough people are questioning it that the controversy becomes impossible to ignore. The newspapers get involved, naturally. There's something about the story that fits too neatly into existing narratives about women in science, about graduate students being exploited, about credit being stolen. Some of the coverage is supportive of Jocelyn. Some treats the whole thing as a curiosity. Some focuses less on the science and more on the human interest angle. Young mother, brilliant discovery, overlooked by the establishment. Jocelyn, for her part, doesn't particularly want to be a symbol of anything. She's a scientist who made a discovery and is now trying to continue her career. But the story has momentum of its own, and she finds herself fielding questions from journalists who want to know, how does it feel? Are you angry? Do you think you deserved the Nobel Prize? And when she finally responds publicly, when she's pushed into giving a statement, she says something remarkable. I believe it would demean Nobel Prizes if they were awarded to research students, except in very exceptional cases, and I do not believe this is one of them. Read that again. Let it settle. She's defending the system that excluded her, not with bitterness or sarcasm, but with what appears to be genuine conviction that this is how things should work. She elaborates in other statements. I was a graduate student and the supervisor gets the credit. A simple observation about academic hierarchy, about how the system is organized, about the way credit flows through the institutional structures of science. There's no anger in these statements, at least not publicly. No sense of injustice or betrayal. No suggestion that she's been wronged. Just a calm acceptance that this is how the world works, coupled with a determination to keep doing her work regardless of whether prizes acknowledge it. Now here's where we need to understand something about the context, about what was considered normal in 1974, and how academic science organized itself. At the time, it was widely understood that graduate students assisted discoveries. They did not make them. This wasn't a secret conspiracy or a deliberate policy to exclude anyone. It was simply how the hierarchy worked, how everyone understood the relationship between supervisors and students. The supervisor provided the theoretical framework, the institutional support, the resources, the scientific direction. The student did the observations, the data analysis, the day-to-day labor. When something important emerged from this collaboration, credit went to the supervisor because they were the one responsible for the overall research program. It was a model that had worked for generations. Newton had students. Einstein had students. Every major scientist built their career partly through the work of junior researchers who learned by contributing to the senior researcher's vision, and the system perpetuated itself because everyone who was once a student eventually became a supervisor, and the pattern continued. Except, of course, for those who never made it to the supervisor stage, for those who left science or who remained in junior positions, or who simply weren't promoted through the ranks for reasons that had more to do with who they were than what they'd discovered. There's also the gender dimension, visible in the pattern but rarely spoken aloud. Women in science often did the work while men received the recognition. Not always, not universally, but frequently enough that it created a clear statistical pattern. The Harvard computers, Lisa Meitner, Rosalind Franklin, Cecilia Payne. A long shadow history of women whose contributions were minimized, whose discoveries were attributed to male colleagues, whose names appeared second or third or not at all on papers describing work they'd done. But here's the complexity. It wasn't just about gender. It was also about the broader question of how discovery itself is defined. Who sees the data versus who interprets it? Who makes the observation versus who understands its significance? Who notices the anomaly versus who explains what it means? In the case of pulsars, Jocelyn made the observation. She noticed the scruff, tracked it, verified it, confirmed it was real. But the theoretical framework that explained what pulsars were, the neutron star model, the lighthouse mechanism, the astrophysics that came from others, Gold and Pacini and other theorists who understood what these objects must be based on existing physics. So the question becomes, what counts as discovery? The seeing or the understanding? The observation or the explanation? And who gets to decide? The Nobel Committee in 1974 decided that Hewish's role in directing the research program and interpreting the significance of the observations constituted the decisive contribution. They weren't necessarily wrong by the standards of their time. They were applying the traditional model of how credit works in academic science. But there's a reason it felt wrong to so many people, even in 1974. Because Jocelyn's contribution wasn't passive. She wasn't just following instructions, dutifully recording data that someone else told her to collect. She noticed something unexpected. She insisted on investigating it when others were dismissive. She did the work of verification that transformed probably just noise into definitely something real. That's not assistance. That's discovery. And yet, the system said otherwise. The hierarchy asserted itself. The traditional model prevailed, and Jocelyn Bell Burnell, with remarkable grace, accepted it and moved on. Think about the compression happening in this moment. A massive star collapses under its own gravity, crushed down to impossible density, transformed into something fundamentally different from what it was. The scale changes, the rules change, everything that seemed solid becomes something else entirely. October 1974 is Jocelyn's compression, the moment when institutional norms meet cosmic truth and somehow cosmic truth comes out looking smaller. When the discovery that changed astronomy gets attributed to the institutional hierarchy rather than to the person who made the observation. This is the gravitational well, the lowest point in the orbit, the moment of maximum pressure, but, and this is crucial, not the end of the trajectory. Because here's what different people do when facing injustice. Some respond with anger, with campaigns, with demands for vindication. Some withdraw, become bitter, let the hurt calcify into resentment. Some fight publicly, making the injustice itself the central story of their lives. Jocelyn does none of these things. She continues her work, moves forward in her career, takes positions at Southampton, continues at University College London, studying X-rays and gamma rays, building expertise across multiple wavelengths of astronomy. The pulsars were one discovery. There's more universe to study, more questions to ask, more observations to make. Her work at the Mullard Space Science Laboratory focuses on high-energy astrophysics, X-ray emissions from celestial objects, the violent processes that produce radiation across the electromagnetic spectrum. It's painstaking work, requiring the same kind of careful attention she brought to those chart recorder papers back in Cambridge. The same discipline of observation, the same willingness to spend hours looking at data that might reveal something unexpected. It's not that she's unaffected by the Nobel decision. Years later, she'll speak more candidly about the disappointment, about what it felt like to watch someone else receive recognition for work she'd done. She'll acknowledge the hurt, the sense of being overlooked, but in the moment, in 1974, her response is essentially, "This is what happened, I'm not surprised by it, and I have work to do." There's something almost stoic about it, the ancient philosophy that emphasizes controlling what you can control and accepting what you can't. She can't control the Nobel Committee's decisions. She can't change the academic hierarchy or the gender dynamics of 1970s science. She can control her own response, her own work, her own integrity. And there's the Quaker dimension too, that teaching about the inner light that remains constant regardless of outer recognition. That emphasis on service over acclaim, on the work itself, rather than the rewards it might bring. She was raised in a tradition that says your worth isn't determined by what others think of you or what prizes you win. It's determined by whether you're faithful to the truth, whether you're doing the work you're called to do. The inner light remains regardless of outer recognition. So she continues, and in continuing, in not being crushed by the compression, she demonstrates something that might be more important than any prize, the ability to persist, to keep doing meaningful work, even when the world fails to acknowledge it properly, to maintain integrity when the system reveals its limitations. The controversy doesn't disappear quickly. It lingers in the scientific community, becomes part of the conversation about how credit should work, about whether the traditional supervisor-student model still makes sense in an era where graduate students are doing increasingly sophisticated research. It becomes a case study in questions about recognition, about who deserves credit, about whether the Nobel Prize, designed in another era for another kind of science, still fits the collaborative reality of modern research. But Jocelyn herself moves forward. The work continues, the career develops, the recognition she does receive, fellowships, medals, positions, accumulates gradually, building a different kind of authority than the one conferred by a single dramatic prize. The Nobel Prize is a moment, an important moment certainly, the highest honour in science, recognition that shapes careers and legacies. But it's still just a moment, a single day in October 1974. The Pulsars, those are forever, or as close to forever as anything in the universe gets. They'll keep spinning long after everyone involved in the 1974 controversy is gone, long after the Nobel Committee that made the decision has been replaced a dozen times over, long after the academic structures that determined how credit should flow have evolved into something different. Somewhere out there, the first pulsar she discovered continues its patient rotation, still pulsing every 1.337 seconds, still broadcasting its signal to a universe that largely doesn't care, still marking time with precision that renders human institutions and their prizes almost quaint by comparison. It doesn't know about the Nobel Prize. It doesn't care who got credit for its discovery. It just keeps spinning, following the laws of physics, doing what neutron stars do. And Jocelyn Bell Burnell, in her own way, does the same. Keeps working, keeps observing, keeps contributing to human knowledge about the universe, regardless of whether prizes acknowledge those contributions. The compression is complete, the pressure applied, but unlike a star collapsing into a neutron core, Jocelyn doesn't collapse. She doesn't break under the weight of institutional oversight. She emerges from October 1974 still herself, still curious, still working, still committed to understanding the universe. The orbit will continue. The trajectory hasn't ended. This is the lowest point, yes, but it's not the final destination, because what comes after compression can sometimes be surprising. What emerges from pressure isn't always collapse. Sometimes it's transformation. Sometimes it's the slow accumulation of a different kind of authority. Sometimes it's the realization that there are forms of recognition more meaningful than prizes, forms of impact more lasting than awards ceremonies. The thing about continuing after being overlooked is that you have to actually continue, not in some metaphorical sense, not as a philosophical principle, but as the daily practice of getting up and going to work and doing the research and writing the papers and teaching the students and navigating the politics of academic science. After October 1974, Jocelyn Bell Burnell does exactly that. She moves through a series of positions, each one adding another layer to her expertise. Southampton first, from 1974 to 1982, working in X-ray astronomy. Then the Royal Observatory, Edinburgh, from 1982 to 1991, expanding into infrared and optical astronomy. It's a pattern common among research scientists, moving between institutions, following opportunities, building breadth of experience across different wavelengths and different questions. What's less common is doing this while carrying the weight of being the person who discovered pulsars, but didn't win the Nobel Prize. That fact follows her. Not oppressively, perhaps, not constantly, but it's there, part of the background radiation of her professional life. Some people know her as the woman who should have won the Nobel. Others know her simply as an accomplished astronomer, working across multiple fields. Both things are true simultaneously. The work itself is methodical, careful, the kind of science that doesn't make headlines, but slowly builds the foundation of understanding. X-ray astronomy in the 1970s and 80s is still relatively young. X-rays from space were only discovered in the early 1960s, and understanding what produces them requires patient observation of exotic objects. Neutron stars, actually. Black holes. The violent processes at the edges of physics. There's a certain poetry in this. Having discovered one kind of neutron star signature, radio pulsations, she now studies another kind, X-ray emissions. Different wavelengths, different physics, but the same underlying objects. Stars that died and became something strange and extreme. At Edinburgh, the work expands further. Infrared astronomy, which sees through dust clouds to observe star formation. Optical astronomy, the traditional kind, looking at visible light. Millimeter wave observations of molecular clouds. She's building expertise across the entire electromagnetic spectrum, becoming not just a pulsar expert, but a broadly capable astronomer who can work at any wavelength. This breadth matters more than it might seem. Science increasingly requires people who can see connections across disciplines, who understand how different kinds of observations relate to each other. Jocelyn is becoming that kind of scientist, not through any grand plan necessarily, but through the accumulated experience of moving between fields and learning to think in multiple wavelengths. The recognition accumulates gradually, not the dramatic kind, no Nobel Prize, but the steady acknowledgement of sustained contribution. The Michelson Medal in 1973, even before the Nobel controversy. The Beatrice M. Tinsley Prize in 1987, recognizing outstanding research contributions by women in astronomy. The Herschel Medal in 1989 from the Royal Astronomical Society. Each award is meaningful. Each represents peers saying, "We see what you've done, we recognize its value." But none of them are the Nobel Prize. None of them quite resolve the question that lingers in the background. Was she wronged, or was the system simply operating as designed? She doesn't dwell on it publicly. In interviews from this period, when asked about the Nobel decision, she's consistent. It doesn't bother her. The system worked as it should have. She was a graduate student, and that's how credit flows. Whether this is genuine acceptance or practiced diplomacy is hard to say. Maybe both. Maybe the line between the two becomes blurry after enough years of saying it. What's clear is that she's building something beyond individual recognition. Throughout the 1980s, she begins serving on committees, advising on policy, working quietly to open doors for others, not through confrontation or activism necessarily, but through presence and example, being the woman in the room, asking the questions that need asking, advocating for students who might otherwise be overlooked. There's a particular kind of authority that comes from having been underestimated and then proving yourself anyway. She has that authority. When she speaks about the challenges facing women in physics, people listen because she's lived it. When she argues for better support for graduate students, she speaks from experience. The Nobel omission, in a strange way, becomes part of her credibility. Students remember her differently than they remember most professors. She's patient with questions, willing to explain things multiple times without impatience, interested in what students think, not just in telling them what to think. It's the teaching style of someone who remembers being dismissed, who knows what it's like to have an idea and watch others overlook it. The astronomy itself continues to fascinate her. This is perhaps the most important thing to understand. She genuinely loves the work. Not the recognition, not the prizes, but the actual practice of studying the universe. The observations, the data analysis, the slow accumulation of understanding. It's not a consolation prize, it's the thing itself. Picture her at a telescope, infrared observations at a mountain observatory perhaps, or analysing X-ray data from a satellite, the same focused attention she brought to those chart recorder papers in Cambridge, the same willingness to spend hours looking for patterns, anomalies, anything unexpected, the same fundamental curiosity about what the universe is doing out there in the darkness. She's not trying to make another pulsar-scale discovery. Lightning rarely strikes the same place twice in science, and she's not chasing it. She's just doing astronomy, contributing to the collective understanding, training the next generation, serving on the committees that keep the scientific infrastructure running. It's unglamorous work, mostly, the kind that doesn't get movies made about it. No eureka moments, no dramatic breakthroughs, just the patient accumulation of knowledge, one observation at a time, one paper at a time, one taught student at a time. But this is what most science actually is. Not the headline discoveries, but the infrastructure of understanding. Not the Nobel Prize moments, but the decades of work that make those moments possible. The careful observations, the rigorous analysis, the teaching and mentoring that trains the people who will make the next generation's discoveries. And slowly, almost imperceptibly, something shifts. She stops being defined primarily by the Nobel omission and starts being known for the breadth of her contributions, the multiple fields she's worked in, the students she's trained, the committees she's served on, the institutional knowledge she's accumulated. There's a particular kind of respect that comes from sustained excellence over time. It's different from the respect granted to prize winners, less dramatic perhaps, but in some ways more durable, because it's based not on a single achievement, but on decades of contribution, of showing up and doing the work, and helping others do theirs. By the late 1980s and early 1990s, she's becoming an elder stateswoman of British astronomy. Not through any official designation, there's no ceremony where they hand you that title, but through the accumulated weight of experience and contribution. People come to her for advice. Institutions want her on their boards. Younger scientists seek her out as a mentor. The work on behalf of women in physics becomes more explicit during this period, not through grand gestures or public campaigns, but through the quiet work of making space for others, serving on hiring committees and advocating for qualified women candidates, speaking at events for female physics students, writing letters of recommendation, opening doors that were closed to her. There's something transformative about this, the experience of being overlooked, which could have led to bitterness or withdrawal, instead becomes fuel for ensuring others don't face the same barriers. It's a form of alchemy, taking the lead of injustice and transforming it into the gold of advocacy. Ancient wisdom traditions often talk about this pattern, the wounded healer, the one who suffered and then uses that suffering to help others. It's not that the suffering was good or necessary, it wasn't. But once it's happened, once you've walked through it and come out the other side, you have knowledge that can serve others walking a similar path. Jocelyn, whether she thinks about it in these terms or not, is becoming that kind of figure. Not a victim of the system, but someone who understands its limitations and works to improve it. Not bitter about the past, but determined to make the future different for others. The institutions recognize this, slowly, managing positions at multiple facilities, leadership roles in professional societies, the kind of responsibilities that go to people who've proven they can be trusted with institutional stewardship. She's good at it. The administrative work, the committee service, the delicate navigation of academic politics. Not everyone is. Many brilliant scientists are terrible administrators, impatient with bureaucracy, frustrated by the slow pace of institutional change. But Jocelyn has that same patience she brought to scanning chart recorder paper, the same ability to persist through tedium, the same understanding that important work often happens slowly, incrementally, without drama. She's also, importantly, still doing science, still publishing papers, still analysing data, still asking questions about the universe. The administrative work doesn't replace the research. It exists alongside it, adding another dimension to her contributions. This is the long middle of a scientific career, not the dramatic discovery years of youth, not yet the full elder statesman period of late career, just the sustained work of building expertise, training students, serving the field, contributing to collective understanding. It's the part that gets compressed or skipped entirely in most scientific biographies because it's not dramatic enough. But it's essential. This is where depth comes from, where breadth accumulates, where you transform from someone who made a discovery into someone who understands an entire field, where you become not just a scientist, but a builder of the infrastructure that supports science. And through it all, the pulsars keep pulsing. Other researchers build on the foundation of Jocelyn's discovery, finding thousands more pulsars, using them to test relativity and map the galaxy, and understand neutron star physics. The field she opened continues to flourish, continues to produce results, continues to advance human understanding of the universe. She's connected to that ongoing work, but at a distance now. It's not her primary research focus anymore. She's moved on to other questions, other wavelengths, other problems, which is healthy, actually. Science needs people who can let go of their own discoveries and trust others to carry them forward. There's a particular kind of generosity in that, the opposite of the researcher who clutches their discovery possessively, who can't bear to see others working in their field. Jocelyn opens her hands and lets the pulsars go, trusts that the scientific community will do interesting things with them, finds satisfaction in watching the field develop, even when she's not the one driving it. By the early 1990s, as she prepares to move into new roles, professor positions, more senior administrative work, she's built something that matters more than any single prize, a career of sustained contribution, a reputation for excellence across multiple fields, a network of students and colleagues who know her as someone who shows up, does the work, helps others, advances the field. The Nobel omission is still there, part of her story, impossible to separate from her biography, but it's no longer the defining fact. It's one fact among many. A moment in October 1974, painful and unjust, but not the final word on a life in science. Because here's what persistence does. It outlasts moments. It accumulates into something larger than individual events. It builds authority that doesn't depend on prizes or awards, but on the demonstrated reality of sustained excellence. The oak grows slowly but stands longest. The patient accumulation of growth year after year, ring after ring, until you have something too substantial to be toppled by individual storms. Jocelyn Bell Burnell, in these decades after the Nobel omission, is growing into that kind of oak. Not through grand gestures or dramatic vindication, but through the simple practice of continuing, of showing up, of doing the work, of being quietly and persistently exactly the kind of scientist the field needs. The compression of October 1974 didn't crush her, and the persistence of the decades after proves something that matters more than any prize, that she's built for the long haul, that she can sustain excellence across decades, across fields, across all the challenges that come with building a career in science. Something happens when you've been doing excellent work for long enough. The accumulation reaches a tipping point. The breadth becomes authority. The persistence becomes platform. And suddenly, though it's not really sudden at all, though it's been building for decades, people start listening differently. For Jocelyn Bell Burnell, this transformation begins in the 1990s and accelerates through the 2000s, not because she changes what she's doing, necessarily, but because the world is finally ready to hear it. In 1991, she becomes Professor of Physics at the Open University, an institution designed to make higher education accessible to people who've been excluded from traditional pathways. It's a fitting position for someone who spent her career navigating barriers. The Open University believes that education shouldn't be reserved for those who follow the expected trajectory, that knowledge belongs to anyone willing to do the work. Jocelyn understands this in her bones. Then, in 2001, Dean of Science at the University of Bath. More administrative responsibility, more institutional influence. The kind of position that goes to people who've proven they can be trusted with shaping the future of their field. But it's in 2002 that something significant happens. She becomes president of the Royal Astronomical Society, the first woman to hold the position in the organisation's 182-year history. Think about that for a moment. An institution founded in 1820, when women weren't even allowed to attend university, when the idea of a female astronomer was considered somewhere between amusing and absurd. And now, in 2002, Jocelyn Bell Burnell is its president. She doesn't make a big deal of being the first. That's not her style. She just does the work, guiding the society, advocating for the field, representing British astronomy to the broader world. But the symbolism matters whether she emphasises it or not. Doors that were closed are now open. Roles that were unthinkable are now normal. During her tenure, she begins speaking more openly about the Nobel decision. Not bitterly, not with the heat of recent injury, but with the measured perspective that comes from 3 decades of distance. She frames it not as a personal grievance, but as an example of structural issues in how science recognises contribution. This is important. She's not saying, "I was wronged," in a way that centres herself. She's saying, Here's how the system worked. Here's why it was problematic. Here's what we might do differently. It's the voice of someone who's moved beyond personal hurt into systemic analysis. The wounded healer, using the wound to help others understand the injury. The articulation is clear. Graduate students make real discoveries. The supervisor model that automatically assigns credit to senior researchers is outdated. Women's contributions have been systematically minimized throughout scientific history. These aren't just her problems. They're patterns that affect everyone who doesn't fit the traditional mold. People listen now in a way they didn't in 1974, partly because she's earned the authority to speak, partly because the culture has shifted enough to hear it, partly because she's not attacking anyone personally. She's observing systems, describing patterns, suggesting improvements. In 2008, she becomes president of the Institute of Physics, again, the first woman to hold the position. It's a pattern now, not a fluke. She's being chosen for leadership roles in the most prestigious scientific institutions in Britain, not as a token, not as a diversity hire, but as someone whose judgment and experience make her the obvious choice. She uses these platforms deliberately, mentoring programs for underrepresented students in physics, speaking events at schools with large populations of female students, working with organizations that support women and minorities in STEM. The advocacy becomes explicit, intentional, strategic. There's a particular quote from this period that captures her philosophy. Science is a collaborative endeavor, not a competition where individuals battle for glory, not a hierarchy where credit flows predictably upward, but a collective human effort to understand the universe where everyone's contribution matters. It's a radical reframing when you think about it. The Nobel Prize model treats science as individual achievement. Here's the genius who made the discovery. Here's the singular mind that changed everything. But Jocelyn's experience, both in making a discovery and in watching how credit got assigned, taught her something different. Discovery happens in context. It requires infrastructure, collaboration, the accumulated knowledge of everyone who came before. The recognition continues to accumulate. In 2007, she's made Dame Commander of the Order of the British Empire, honorary doctorates from universities around the world, more than 30 of them eventually, medals from scientific societies recognizing lifetime achievement, each one acknowledging not just the pulsar discovery but the decades of contribution that followed. In 2015, she's appointed Chancellor of the University of Dundee. It's a ceremonial position primarily, but it puts her in a role of symbolic leadership for an entire university. And she uses it the way she's used every platform, to advocate for accessibility, for diversity, for opening doors that have traditionally been closed. She's still giving lectures on pulsars, still explaining neutron star physics, still sharing the story of that summer in 1967 when she noticed the scruff. But now she also talks about what happened after, about the Nobel decision, about building a career anyway, about transforming exclusion into advocacy. And then, in 2018, something remarkable happens. The Special Breakthrough Prize in Fundamental Physics is awarded to Jocelyn Bell Burnell, $3 million. One of the most generous prizes in science, awarded specifically for the discovery of pulsars, the work that didn't win the Nobel Prize 44 years earlier. The Breakthrough Prize is relatively new, established by tech billionaires who wanted to celebrate scientific achievement with the kind of money and publicity usually reserved for entertainment awards. It's sometimes called the Oscars of Science, complete with televised ceremonies and celebrity presenters. $3 million is real money, more than the Nobel Prize, actually. Picture that moment, 75 years old, decades past the discovery, finally receiving major recognition for the work that changed astronomy. Many people would treat this as vindication, as the moment when justice is finally served, when the wrong is made right, when she can say, "See, I told you so," to everyone who doubted. Jocelyn Bell Burnell does something different. She gives it away, all of it, the entire $3 million, not to charity in some abstract sense, not to her university or to some general scientific fund. She creates the Bell Burnell Graduate Scholarship Fund, specifically designed to support graduate students from underrepresented groups in physics: women, ethnic minorities, refugees, the people who face the same kinds of barriers she faced, the people who might be overlooked the way she was overlooked. Her reasoning is characteristically direct. I don't want or need the money myself, and it seemed to me that this was perhaps more useful to young people entering astronomy who don't have stable financial circumstances. Read that again. She doesn't want or need the money. After decades of watching others receive credit for her work, after finally getting a major prize, she redirects it entirely toward the future, toward people she'll never meet, working on problems she'll never study, making discoveries she'll never see. This is the emotional climax of the story, not the discovery, not the Nobel mission, not even the breakthrough prize itself, but what she does with it, the choice to transform personal recognition into collective support, to turn vindication into service. It's the fullest expression of those Quaker values she absorbed as a child, the inner light made visible through action, service over acclaim, using resources to help others rather than accumulating them for yourself. The belief that your worth isn't measured by what you own or what prizes you've won, but by what you do with whatever you've been given. The response to this gesture is overwhelming. The scientific community recognizes it as something extraordinary, not just generous, but transformative. She's not just helping individual students. She's making a statement about what matters, about how we should think about recognition and resources and responsibility. Ancient wisdom traditions talk about this kind of alchemy, taking what was meant to hurt you and transforming it into healing for others, taking the lead of injustice and turning it into the gold of opportunity. The philosopher's stone isn't a magical object that transmutes metal. It's the wisdom that transmutes experience into service. Jocelyn has found that stone, or maybe it was there all along, planted in childhood, cultivated through decades of patient work, finally revealed in this moment when she had the resources and the platform to do something truly transformative. The recognition continues after the Breakthrough Prize, the Royal Medal in 2015, the Copley Medal in 2021, the Royal Society's oldest and most prestigious award, previously won by Darwin, Einstein, Hawking. It's given for outstanding achievement in research in any branch of science. She's now in the company of the people who shaped how we understand reality itself. But here's what's interesting. These late career awards don't feel like compensation for the Nobel mission. They feel like recognition of something larger, the complete arc of her contribution. Not just the discovery, but everything that came after. The breadth of her work, the students she trained, the doors she opened, the scholarship fund she established, the voice she developed and the way she used it. The transformation is complete, from overlooked graduate student to elder stateswoman, from the person who made the discovery to the person who changed how we think about discovery, from someone denied recognition to someone who uses recognition to serve others. She speaks at this point with an authority that comes not from anger or vindication, but from having walked the entire path, from knowing what it's like to be dismissed, to persist anyway, to build a career despite obstacles, to finally receive recognition and then give it away. She's earned the right to speak about how science should work, about who gets credit and why, about what we owe to the next generation. And people listen, not just because she's famous, though she is now, not just because she discovered pulsars, though that matters, but because she's demonstrated wisdom through action, because she's shown that there's a way to respond to injustice that's neither acceptance nor bitterness, but transformation. There's a quote from her about the Nobel situation that captures this evolution. Years after the initial "it doesn't bother me" statements, she says something more nuanced. "I've had more mileage out of not getting a Nobel Prize than Hewish got out of getting one." It's said with humour, not bitterness, and it's true in a way that goes beyond what she probably meant. The Nobel omission became part of her story in a way that made her more influential, not less. It gave her credibility when she spoke about systemic issues. It made her an example of grace under pressure. It created the conditions for that moment in 2018 when she could give away $3 million and make it mean something. The widening continues into her 80s. Still active, still speaking, still advocating. The Bell Burnell Scholarship recipients are starting their careers now, funded by that $3 million. Some of them will make their own discoveries. Some will face their own barriers. All of them carry forward the example of someone who transformed exclusion into opportunity. This is what the long game looks like. Not winning by traditional measures, she still didn't get the Nobel Prize. That fact doesn't change. But building something that matters more than prizes, creating impact that ripples forward through time, touching people she'll never meet, enabling discoveries that will happen long after she's gone. The pulsars keep pulsing. Thousands of them now catalogued, studied, used as cosmic tools in natural laboratories. The field she opened continues to flourish, and the students funded by her scholarship continue the work, adding their own contributions to humanity's understanding of the universe. From compression to persistence to widening, from the gravitational well of October 1974 to the expanding influence of a life well lived. The orbit didn't end at the lowest point. It continued, building momentum, reaching towards something that looks less like vindication and more like transcendence. Not transcendence in some mystical sense, just the simple, profound reality of choosing service over recognition, choosing to give rather than accumulate, choosing to use whatever platform you've earned to help others rather than to settle scores. The Quaker girl from Belfast, who failed the 11+ exam, who built a telescope with her own hands, who noticed a 1/4 inch of scruff and changed astronomy, who watched someone else win the Nobel Prize, who kept working anyway. She's become something remarkable, not despite the obstacles, but somehow through them. Not because justice was served, but because she chose a different definition of justice. One that measures success not in prizes accumulated, but in doors opened, not in recognition received, but in opportunity given, not in vindication claimed, but in transformation enacted. Today, as you're listening to this, pulsars are still being discovered. More than 3,000 of them are catalogued now, scattered throughout the Milky Way like cosmic buoys marking the locations where massive stars once lived and died. Each one spinning, broadcasting, marking time with precision that will outlast everything humans have ever built. The technique Jocelyn developed in 1967, patient observation of radio signals, careful attention to anomalies in the data, remains foundational to radio astronomy. Modern telescopes are vastly more sophisticated than that 4-acre array she helped build at Cambridge. They're more sensitive, more precise. capable of detecting fainter signals from farther away. But the fundamental approach is the same. Listen carefully, notice patterns, investigate what doesn't fit. And pulsars have proven to be even more useful than anyone imagined in 1968. They've become tools for studying physics that goes beyond anything we can test in laboratories. Take pulsar timing arrays. Astronomers monitor dozens of pulsars simultaneously, watching for tiny variations in when their pulses arrive. Because pulsars are such stable clocks, any deviation from their expected rhythm tells you something is affecting the space between here and there. And in 2023, pulsar timing arrays detected something extraordinary. Gravitational waves from supermassive black holes billions of times more massive than our Sun, creating ripples in space-time itself. The universe, essentially, is using pulsars as a galaxy-scale gravitational wave detector, something that exists naturally, that we didn't build, that works better than anything we could construct. And we can use it because Jocelyn Bell Burnell noticed a quarter-inch of scruff in 1967. The Hulse-Taylor binary pulsar, discovered in 1975, provided the first indirect evidence for gravitational waves. Two neutron stars orbiting each other, their orbits slowly decaying as they radiate energy in the form of gravitational waves. Exactly as Einstein's theory predicted. Russell Hulse and Joseph Taylor won the Nobel Prize in Physics in 1993 for that discovery. They found their pulsar using techniques developed from Jocelyn's work, studying objects that exist because she proved they were real. In 2017, the Nobel Prize in Physics went to Rainer Weiss, Barry Barish, and Kip Thorne for the direct detection of gravitational waves using LIGO. The waves they detected came from colliding black holes, but the theoretical framework and observational techniques built on decades of pulsar research. Every gravitational wave detection stands on the foundation of knowing that neutron stars exist, that they can be detected, that they can be used as cosmic laboratories. Jocelyn is in her 80s now, still active in astronomy and advocacy, still giving talks, still serving on committees, still working to make physics more accessible to people who don't fit the traditional mold. The Bell Burnell Scholarship recipients are starting their careers, beginning to make their own contributions to science. The pulsars themselves continue to surprise us. They're being used for navigation now. X-ray pulsar navigation for spacecraft, using these cosmic lighthouses as positioning beacons when you're too far from Earth for GPS. They're probing dark matter, measuring how the galaxy's invisible mass affects their signals. They're testing fundamental physics in ways that weren't even conceivable in 1967. Some applications sound like science fiction, using millisecond pulsars, ones spinning hundreds of times per second, as the most accurate clocks in the universe, better than anything humans can build. Watching binary pulsars as natural laboratories for testing how matter behaves at nuclear densities. Studying magnetars, pulsars with magnetic fields so intense they tear atoms apart, to understand physics that can't exist anywhere else. The universe keeps validating her work, not through prizes, but through utility, through the way her discovery keeps enabling new science, keeps opening new questions, keeps proving useful in ways nobody predicted. The first pulsar Jocelyn discovered, still officially designated PSRB 1919+21, though everyone calls it the Bell Pulsar, or the Burnell Pulsar now, continues its patient rotation. Every 1.337 seconds, its lighthouse beam sweeps past Earth. That pulsar doesn't know about the Nobel Prize, doesn't care who got credit for discovering it. It's just physics, following the laws that govern collapsed stars, doing what neutron stars do. They endure. They signal. They mark time. Thank you for spending this time exploring a life shaped by attention and patience, and for drifting through a story about what endures. If these quiet journeys through space and science resonate with you, a gentle like helps others find their way here. And don't forget to subscribe to The Sleepy Astronomer. Sweet dreams, fellow travellers through space and time. Rest well knowing that somewhere out there stellar remnants are still spinning, marking time in the dark. Good night from The Sleepy Astronomer.